Lesson 52. I will say, the nice part of having my prep first hour is some of my technology I try and get ready, and it gives me a little extra time when it all backfires like today. So, okay. Lesson 52, maximization and minimization problems. Say that 10 times fast. Maximum and maximization and minimization problems. We are talking about, we're looking at maximums and minimums, and we can use derivatives to solve these. Okay. We'll talk about critical values. I guess if you read up there, maximum and minimum value problems can be solved by using derivatives. The critical values will determine relative maximum or minimums.
I think we should get extra credit for being able to say it right.
And these will then be the answers to some of life's trickiest problems. These problems can also be done by graphing the original equation and finding the max or min values on a calculator. Okay? So, and part of it will also be, once we get our critical values, keep in mind we'll have to show that it is a maximum or a minimum. Okay, we can't just assume that that is the maximum or that is the minimum. You have to be able to show, and that's using like our first and second derivative test from the other day. So, Mr. Wallen has 100 yards of fence. He wants to form a rectangular field enclosed on 3 sides by the fence and on 1 side by a river whose banks are straight. Find the greatest area that the fence can enclose. Funny enough, we were talking about band the other day. My high school band director was Mr. Wallen. Spelled differently, but Trevor mentioned Mr. Wallen to your mom, and she'll know.
Do it right now. Just say Mr. Wallen in the text.
Okay, that might confuse her. Okay, so let's get the idea here. Mr. Wallen has what? 100 yards of fence. He wants to form a rectangular field enclosed on 3 sides by the fence and 1 side by a river. I feel like that's a traditional calculus problem. Yeah. No. Okay. Final goal is to find the greatest area that the fence can enclose. Okay. So I want a rectangular field. Here's my rectangle for my rectangular field. It specifically says on 1 side by a river. So I'm going to make this bottom side a little thicker there and longer. And noting that side is a river. So that side is not fenced. It is surrounded by the river. So I guess whatever he's enclosing in this fence is not going to cross the river. Or the river's too big. I don't know. Okay. We're trying to find the greatest area that this fence can enclose. What do you know about area of a rectangle? Length times width, yes? Now, with this in mind, we generally will think length times width. I'm trying to think how I want to put this down. We can say L and W. I'm actually going to use X and Y here. But the key is, when we write that area equation, are we going to want to have 2 variables? And no, we're going to want to have this all in terms of 1 variable. So I'm going to suggest that X be our width. Now, keep in mind, if X is our width at the right-hand side, then X is also our width at the left-hand side, right? For the moment, I'm going to think of that as Y. Okay. But we really need to talk about what the length of that side is in terms of X. And what can we use to help us figure that out? We were given the fact that there are 100 yards of fence. How does this play into things if there's 100 yards of fence? Perimeter of the 3 sides. So the idea that side X plus what I'm currently calling side y has to equal 100. Does that make sense? What can I do with this equation? Yeah, essentially make it y equals, subtract 2x. I will say that x plus x is 2x plus y equals 100. And then if you are solving for y, realize that is going to be y equals, I'm going to say 100 minus 2x. If you'd prefer, you could say negative 2x plus 100. And what do we know about this 100 minus 2x? It's y. It's that third side, yes? Okay, so my goal is to maximize area. I'm trying to find my greatest area, which means ultimately I need an area formula. So I'm going to say area. I'm actually going to say A of x because it's all going to be terms of x. What's my area here? Okay. We normally would say x minus y. In terms of x, we're going to say x times 100 minus 2x. Go ahead and multiply that for me because you're going to want it multiplied for your next step. What is x times 100 minus 2x? 100x minus 2x squared. Okay. In order to maximize via calculus methods, we want to take the derivative and find our critical values, which max or min, right? So, a of x is 100x minus 2x squared. What's a prime of x? (100 minus 4x). How do we find our critical points? Set it equal to 0. So 100 minus 4x equals 0. Solve it. Negative 4x equals negative 100. X equals 25. So, that right there, x equals 25, that is the place where my, just for notation's sake, excuse me, my first derivative equals 0, right? So the idea that if I say a prime of 25, the first derivative equals 0. Critical value, so that is either a maximum or a minimum. Our assumption is it's going to be a maximum because they're asking us to find the greatest area, right? And so we're kind of assuming it's a max. You could look, we still have to prove it, but to feel a little more validated, look at your original function. It was 100x minus 2x squared. If 2x squared is my highest power, what's that graph look like? Parabola, but negative 2 makes it upside down. So does that make sense that it has a max? Yeah. Now, ways to tell that it's a max. We could look at values on either side of it. We can also use our second derivative test. Let's look at the second derivative for a moment. Sorry, I got a tickle in my throat. What's the second derivative?
Negative.
I agree. The second derivative is negative 4. Because, so, officially I can ask you, what is the second derivative at the value of x equals 25? But the value of the second derivative is always negative 4, yes? Since that second derivative is negative, Daryl just said it, a second derivative that is negative tells me that it is concave down at that point. So, second derivative negative is going to mean concave down. If something is concave down, does that give you a min or a max? Concave down is going to mean a max. So that's using the second derivative test by mentioning that that second derivative is negative at the critical value. Okay? Now, what did the question actually ask us?
What is the greatest area?
Find the greatest area. So am I done?
No.
No. I found where the greatest area is. How do I find the greatest area? Plug 25 in for x to find y. Where? Now, 2x plus y equals 100 was perimeter.
Okay, 25 is the length.
25 is the width. Oh, I see what you're doing. Ah, okay. Okay. Got it. You were saying plug 25 in here. That gives you the width, and then you do 25 times the width. Got it. Okay. That works. I was just going to say take 25 and plug it into my area equation up here. Now, is that really a whole lot different than what Nathan's doing? It's just a difference in thinking process, but it's the same idea. My question, the reason I asked where are you plugging it in, as in don't fall for the lapse of, oh, I'm going to plug it into one of the derivatives. That was my concern, is that we are going back to the original problem. But here's the deal. Would that work? That would work. I mean, okay, so x times 100 minus 2x. So 25 times 100 minus 2 times 25. So it's going to be 100 minus 50, so 50 times 25. 1,250 what? Squared. Yards squared because we were finding area, not volume. Okay. Ready to try example 2? Example 2. Find two positive numbers whose sum is 8 and whose product is a maximum. Two positive numbers whose sum is 8. How can you write that? You guys okay with x plus y equals 8? So x and y are positive numbers, their sum is 8. And whose product is a maximum. How do we write an equation for that one? We don't know what the product is, so I can just use, I was just going to use P for product. Okay? So just, a generic variable, because hopefully you see derivatives coming into play here. Okay? So the product is x times y, right? Those two positive numbers that we used x and y for. Do I want to take the derivative right now? No. We want to work to get this equation in terms of one variable. How can I get the equation? Because what we're trying to do is we're trying to maximize the product. So I need to take the derivative of the product, but I don't want to do it until I have one variable.
Subtract one of them over to the east side and then substitute it in.
Okay, we have this connecting equation right here, yes? If x plus y equals 8, I'm going to say y is equal to 8 minus x is my preference of ways to go. It doesn't matter. You're going to take that value and plug it in. So now my product equation becomes P equals x times 8 minus x. Okay, there we go. What should I do with that? Go ahead and distribute. So 8x minus x squared. Now what? Yeah, we got to do the derivative. We've got to find our min or max. So, P prime, what is the derivative of 8x minus x squared? 8 minus 2x. What do I do with that derivative? Set equal to 0. So 8 minus 2x equals 0. Negative 2x equals negative 8. X equals 4. So at this point, we know that P prime of 4, the derivative at 4, is equal to 0. Since the derivative is equal to 0, we know that this 4 is a it's a critical point. Officially, this critical point could be a min, max, or IP. So this is why you don't just stop here. We have to kind of prove it. How can I prove it? Yeah, we can use the second derivative test again and prove it that way. So, what's the second derivative of 8 minus 2x? Negative 2. So then officially, we're trying to figure out what the second derivative is at 4. When you plug 4 into that equation that has no variable, it's still going to be negative 2. And what's important to notice about that second derivative? It's negative. And because it's negative, that means that we are talking concave down. When a graph is concave down, it creates a local maximum. And so, what did the question ask us? 2 positive numbers. So we already know one of them is 4. So x is 4. What's the other one? 4. Well, I will tell you, when you are trying to maximize something in this situation, it is very common that your maximum is actually a square. Does that make sense? Okay. On the first problem up above, we had 3 sides, not all 4 sides. But when you have 2 positive numbers and you're talking about a sum and a product, and you're trying to maximize that product, and you're trying to, say, maximize a rectangle or something, it very often works out to be a square. I won't say always, because there's a lot of things that, come into play, but. Okay. One more problem? Okay. Make an open-top cardboard box by cutting squares, X inches on a side, from each corner of a 12 by 15 inch piece of cardboard and folding up the edges. Find the value of X that results in the largest possible volume and find the volume of that box. Largest possible volume. So what are we trying to find? A maximum again. You do realize, I guess I realize there's no minimums on this page. A minimum will work the same way though. It's just more often than not we tend to maximize things. Okay. I like to draw a picture. You guys have seen this picture before, yes? A piece of cardboard, you cut out the corners to make a box top, a lid, an open top box, I guess is what they called this one, wasn't it? Okay. Rectangle. And